Hello everyone, welcome to lesson number 20. This is Extrema with the first and second derivative test for calculus. I just want to say that in this video we are going to talk about how to find out whether something's increasing, decreasing, a function is concave up or concave down using algebra. What we have done prior to this is use graphs to talk about whether f of x is increasing or decreasing given a derivative graph or what's happening with concavity based on the derivative graph. Here we're going to look at it based on simply algebra. Okay, so if you guys can see right here, and this is stuff just as a quick review, that if our first derivative is greater than 0, okay, that means our rate of change is positive, then our f of x is increasing. That should make sense because our slope is positive, right? This derivative is f prime of x, right? It's a rate of change. If my first derivative is less than 0, that means that f of x is decreasing, right? We're going down. And then obviously if our first derivative is 0, we have a point of a horizontal tangent at y equals 0. So our function is constant. So that's really important to see when we're looking at these graphs. You guys can see visually local maxes, local mins, absolute max, absolute min. We're going to get into this with the actual algebra here in a little bit. But for max or min, a max or min, especially a relative max or min, which is also called a local max or min, you're going to see that the derivative is actually 0, right? We actually have horizontal tangent lines here, which means that our derivative is 0 there. And then the changing of our direction, right? So our slope going positive to negative, negative to positive, is how we're going to figure out which one is which. So all that will be explained when we actually do the questions. Let's go ahead and look at the first 3 examples. So it says, find the intervals for which f of x equals x cubed minus 3x squared plus 5 is increasing or decreasing. So one of the things that I like to do initially when we do these problems is figure out, what derivative test we're looking at. We have a first derivative test and we have second derivative test. So when I'm asking where my function is increasing or decreasing, I literally am looking at my function and I'm like, okay, so when my function is increasing, as you guys can see right here, that just means that my slope, all right, is positive, but more so my rate of change is positive, which means my derivative is going to be positive. So on this interval, from here to here, my derivative should be positive. And then likewise, if I'm coming down here, my slope is going to be negative. So if I'm going from here to here, I know my slope is going to be negative. So I just got to look at this and say that this is a first derivative test. So I know that this is where I have to find f prime of x. And so that's exactly what I'm going to do. So we're going to find f prime of x. So whenever you're asking whether a function is increasing or decreasing, you're going to find the first derivative. And then we're going to set this thing equal to 0. Because first of all, we want to know where it's, where we actually have a horizontal tangent. So where is it not increasing or decreasing? Because remember, when f prime of x is equal to 0, then it's actually constant. It's not increasing, it's not decreasing. So I can go ahead and pull out a 3x. I'm left with an x minus 2 equals 0. So I know that x equals 0. So at x equals 0, this graph is constant. And at x equals 2, this graph is also, the slope is actually, it's not increasing or decreasing. It's level. For a second. Now, I want to know where it's increasing or decreasing. So this is another thing that I have my students do is we want to create a number line, and we're going to use these are all called our critical points, our critical values. And so our critical values are 0 and 2. And we want to plug into the first derivative. We want to know what's going on with the behavior of this graph. So f prime of x is what we want to look at. So I always have my students label the number line here and also put in what we're plugging into, because sometimes we're plugging into the original, sometimes we're in the first derivative, sometimes we're in the second derivative. So it's really helpful to again acknowledge that increasing and decreasing is a first derivative test. And so we're going to plug these values that we're going to find back into this function and not in here. So in between 0 and 2 is 1. So I can plug in 1 here. I don't care what the value is. All I care about is the sign. So if I plug in 1 here, I'm going to get a positive number. If I plug in 1 here, I'm going to get a negative number. So positive times a negative is actually going to give me a negative value. And so there's no double roots here. So I know that this is going to be positive, this is going to be positive, but just, we can just double check here. So anything to the right of 2, so let's look at 3. So if I plug in 3, I get a positive 1. Here I get a positive 9. So positive times a positive, again, is positive. And then if I plug in something like a negative 1, this is going to give me a negative, and this is going to give me a negative, which is going to give me a positive. So I have done all I need to do, ladies and gentlemen, to answer this question now. So whenever f prime of x is positive, which we've also talked about right here, so whenever f prime of x is positive, which is what you see right here, so here we go, positive here, and we're positive here, then I know that my function is increasing. So I can say that f of x is increasing on the interval from, and again, this is not a particle motion question, so we can be in negative infinity. So from negative infinity to 0, and then also from 2 to positive infinity. So we're going to be increasing. So if you guys were to take your calculator and actually graph this thing, you would actually be increasing. You'd be going up the curve from negative infinity to 0, and then you'd be going up the curve again from 2 to positive infinity. And then I'm going to be decreasing here. I'll be decreasing whenever our derivative is negative, so that's going to be from 0 to 2. Okay? So there we go. That is our very first example, pretty straightforward on how to find whether something's increasing or decreasing. So remember, this is a first derivative test. So if you guys look at example number 2, it says find local maxes and mins. Okay, so now we want to look at a local max and min. Well, that's also a first derivative test. And I'll be honest with you guys, I can easily find the max and min of this problem based on all the work that we just did. So these two questions are grouped together because no matter which question I'm asking, whether it's increasing or decreasing or there's a local max or min, you're going to be doing the exact same thing. So we're going to do the same thing that we did over here. And then we're going to come up here and actually find the max and min of this graph, or this function, I should say. So first thing we're going to do is, again, it's a first derivative test. So I'm going to go ahead and find my first derivative for my function, and this is going to be 1 plus 2 cosine of x. And notice, guys, that I'm on the interval from 0 to 2 pi. This is very common. This is very common, so that just means that's going to do one full unit circle rotation. And so, again, just like before, we're going to take our derivative and we're going to set it equal to 0. And we're going to solve for x. We want to know what x is. So we're given that cosine of x is equal to negative 1/2. Well, cosine is negative in quadrants 2 and 3, and the family of where cosine is 1/2 is pi over 3. So I know that x is going to be equal to 2 pi over 3 and 4 pi over 3. All right, so those are our unit circle values that we want to have for that. All right, so those are, again, our critical values. Now, again, cosine of x is equals negative 1/2 in an infinite amount of angles. It's just, again, we're looking at just from 0 to 2 pi. If this had just been 0 to pi, then we would have just looked at this at just 2 pi over 3. Okay, so then what we're going to do is we're going to go back and plug in we're going to do our number line with our critical values. And one thing that I just want to just immediately do with this number line is, since now we are bounded, right? We are bounded here. I want to go ahead and bound my number line as well. That way you don't miss any points if you don't want to say negative infinity, because we're only looking at this from 0 to 2 pi. So I'm going to bound my thing from 0 to 2 pi. And now I'm going to plug into my derivative, right? I'm going to plug into my derivative. And so the easiest thing I want to imagine here is something in the first quadrant, right? So if I plug something in the first quadrant here, I'm going to get a positive number and a positive number. So I'm going to get something that's positive. Now you guys know very well that anything between quadrants 2 and 3, right, this cosine is going to be negative. And so since 2 is greater than 1, this is going to be a negative value. And then over here, we're moving back to quadrant number 4. And so quadrant 4 cosine will be positive, and so this thing right here will be positive. And you could essentially, if you want to, plug in actual unit circle values in these ranges to figure this out, but this is how it's going to work. Now you guys can see this is exactly what we have right here. So if I ask you guys where this is increasing, you would say that where g of x is increasing, you'd say from 0 to 2 pi over 3, and you'd say from 4 pi over 3 to 2 pi, and you'd be absolutely correct. Decreasing would be from 2 pi over 3 to 4 pi over 3. But I'm asking for a local max and min. So this is what I like to do. I want students to realize that from 0 to 2 pi over 3, I'm actually increasing. So I'm going to kind of just go ahead and sketch just some random curve where I'm just increasing. And then remember, at 2 pi over 3, that's a critical value. I know my derivative is 0. So I'm going to start tapering off here. And then from 2 pi over 3 to 4 pi over 3, and again, it doesn't matter how far down I go. I'm just going to I'm starting to decrease. And then at 4 pi over 3, I'm starting to level off. And then I'm going to start increasing again. And so looking at this value, guys, you can see that this is kind of the general idea, the shape of what our graph is going to be. So I know that I have, again, you can see these tangent lines right here, these horizontal tangent lines. So you guys can see that since I went positive to negative, so my derivative behavior went positive to negative, I have a local max or a relative max. So I have a relative max at x equals 2 pi over 3. And you can write local or relative here. It's the same thing. The justification for this is going to be that f prime of x changes signs from positive to negative. Okay, from positive to negative. You do need to justify. You just can't say f prime of x changes signs. You need to say it's from positive to negative, because on the other side of this, on the flip side of this, you guys can see that here we're decreasing, right? And then all of a sudden we start increasing. So you guys can see there's a relative minimum there. So there's a relative minimum at x equals 4 pi over 3. And again, our justification for this is that f prime of x will change the signs from negative to positive. And so up here, you guys can see I'm going up, I'm leveling off, I'm going down, and then I'm going to start increasing again. So at x equals 0, I get a relative max. At x equals 2, I get a relative min. And if anyone's asking, like, what's the justification for what here? Well, the justification for that is right here. So when f of x is increasing, you would just simply say that f double prime of x is positive. And then when f of x is decreasing, you just say f prime of x is actually less than 0. So I probably should have said that at the very beginning. But yeah, this is the justification that you would use for these two questions. All right, so there we go for that. I think this is actually a good stopping point for this video, because I've just done, two very common first derivative tests. I want to say that in this, in these two instances, you could actually do the question one time, and then in this method, and answer whether the function is increasing, where it's decreasing, where there's local max and a local min. So just finding the first derivative, finding the critical values, and doing a number line tells you all four of these things. So that's actually pretty awesome to do. That's very telling for this example, I should say. So I'll see you guys in the next video when we continue doing first derivative test, and we'll do some second derivative tests.